Okay, so we are now here for a new COMSOC video seminar. The first speaker is Julia Stoyanovich. And Julia, please share your screen and the floor is yours.
Thank you very much, Vincent. And thank you everybody for having me here. And as I was telling folks who were here early, this is the last week of the semester and I was grading until 2 a.m. So please bear with me if I suffer a brain freeze. All right, so today it's my pleasure to present to you a recent work called Algorithmic Techniques for Necessary and Possible Winners. I'm Julia Stoyanovich from New York University, and this is joint work with a wonderful and diverse and large group of co-authors. Most of them are here, and they will answer your questions if I can't. They are Vishal Chakraborty, Theo de la Mazur, Benny Kimmelfeld, Fokion Kolaitis, and Kunal Relia. This is part of the work that Fokion, Benny, and I are leading with funding from the US National Science Foundation and the US-Israel Binational Science Foundation, BSF, under the title of DB plus COMSOC, that is Databases Meet Computational Social Choice. Members of our team individually and collectively have been working on a variety of topics that surround the modeling and analysis of preferences under incompleteness and uncertainty. And there's of course a very close connection between preference aggregation in particular and voting. Voting is a kind of preference aggregation. The idea here is not simply that we all are database people, as is conspicuous, and that we are now all suddenly interested in computational social choice, and particularly in voting. Importantly, and this may not immediately meet the eye, we also represent a mix of research styles within databases. Fokion and Benny have done seminal work on database theory with very concrete and beautiful applications, while my focus is on database systems. And this combination of perspectives of looking for a synergy between theory and systems is a hallmark of data management research in general. And this is perhaps the main point that we would like to bring to the COMSOC community as well. And I'll spend the remainder of my time discussing a specific recent paper by our team. On behalf of my co-authors and myself, I'll say that we see this work as the beginning of a DB plus COMSOC conversation. We're looking forward to connecting with you on this and on any other topics at the intersection of our research interests and methodological toolkits. So to start, to motivate the problem, let us consider the mayoral election in New York City. We have lots of candidates, and I'm showing here 4 of the front runners for the Democratic primary. They are Andrew Yang, Maya Wiley, Scott Stringer, and Raymond McGuire. Folks, voters, whom I'm calling here Alex, Beth, and Carl, are going to be casting their votes for the candidates that they prefer. And these votes may be incomplete. So Alex may say that he prefers Wiley and McGuire to Yang and Stringer, but Alex doesn't specify any further preferences. Beth may only say that she prefers Maya Wiley to Raymond McGuire. And Carl may say that Yang is his favorite candidate as preferred to Wiley and Stringer, and he does not express a preference on the remaining candidate. Now, what we can do is take these incomplete statements about preferences and complete them into full orders over all 4 candidates. So I'm showing here one set of possible completions. Each of these is consistent with the partial orders, the partial preferences that each of the voters gave. And now to run an election, we are going to settle on a scoring rule. We're going to use a particular positional scoring rule to approval. And according to this rule, we are going to assign scores, a score of 1 to each of the top 2 scoring candidates for each voter. And then we will add up these scores across voters. And you will see the final scores here in my very small database at the top right. So Wiley and McGuire both have scores of 2, and Yang and Stringer have scores of 1. So in this completion of the voters' incomplete voting preferences, we have Maya Wiley and Raymond Maguire as the co-winners. Now I'm going to make my setup that I illustrated here more formal. We are discussing voting profiles in which we have candidates, M candidates, C1 through Cm, and N voters, V1 through Vn. The preference of a voter is a linear order over the candidates in C. A complete voting profile is a tuple of linear orders with one linear order T1 through Tn corresponding to each voter. And each of these is an order over the candidates. A partial voting profile is a tuple of partial orders, and these are the ones that we see. We see an example here of Alex's partial order and a completion. A completion of a partial voting profile P is a complete voting profile T such that each TL is a valid completion of the corresponding PL. From this, we move on to elections and winners. And we do this with the help of voting rules. A voting rule maps a complete voting profile to a set of winners. Our focus in this paper is on positional scoring rules that are specified by a scoring vector of non-negative integers, S1 through Sm, one for each position, applied to a complete voting profile. The score of a candidate C under some rule R is the sum of scores that C receives from each TL. And we say that candidate C is a winner if its score is at least as high as that of all other candidates. And so we admit co-winners. An example that we already saw is to approval, with the scoring vector of 2 ones followed by zeros for the remaining positions. What we focus on here is how to determine winners in the case of profiles that are incomplete. We are going to use the formulation of Konchak and Lang from 2005. Given a partial voting profile P, a candidate C is going to be called a necessary winner if C wins in every completion of P. And we will call C a possible winner if there exists a completion in which C wins. More formally, the necessary winner problem, or NW as we will denote it, is given a positional scoring rule R, a partial voting profile P, and the candidate C, is C a necessary winner? And similarly, the possible winner problem, PW, is given a positional scoring rule, a partial voting profile, and a candidate. We want to know whether C is a possible winner. A partial voting profile, partial voting profiles can come in different forms. And the complexity of necessary and possible winners has been determined by a series of papers that are listed here. It was shown that NW is in P for every positional scoring rule, and that PW is in P specifically for plurality and veto, and NP complete for every other positional scoring rule. So the question that we want to ask here is, what about different types of partial profiles? And specifically, we will consider two types of such profiles, partial chains, or PC, and partition preferences, or PP. An example of a partial chain is given on my slide. It's the preference of Beth in pink. And an example of a partitioned preference is the preference of Alex in green. A partial voting profile is a partial chain if it consists of a linear order on a non-empty subset of the candidates. An example is the profile of Beth. She prefers Wiley to Maguire, but does not express a preference for any of the other candidates. We also considered partitioned preferences that relax the notion of a total order by requiring that there is a total order between sets of incomparable elements. More precisely, we require that all candidates be partitioned into disjoint subsets, that candidates within a partition be incomparable, but that there is a total order among the partitions. An example is the voting profile of Alex, marked in green, and partition preferences are known to be common in many real-life datasets, and they have been used for learning statistical models, for example, on full and partial rankings, and so we will refer to these two common and useful profile types here. So what do we know about the complexity of necessary and possible winners for different types of preferences? In 2019, Batya Koenig established a near complete classification of the complexity of possible winner, PW, for partitioned preferences for pure positional scoring rules. And in particular, if the rule is the two approval rule, then PWPP is solvable in polynomial time. And in fact, distractability holds for all two valued rules. That is positional scoring rules in which the scoring vector contains just two distinct values. If R is the border rule, however, then PWPP is NP complete. There are also several interesting special cases of partition preferences. Namely, they contain doubly truncated ballots as a special case, where there's a complete ranking of top elements, a complete ranking of bottom elements, and all remaining elements between the top and the bottom are pairwise incomparable. This model, for example, is the setting in which a voter has complete rankings of some top candidates and of some bottom candidates, but is indifferent about the remaining candidates in the middle. Doubly truncated ballots contain top truncated and bottom truncated ballots as special cases. And as the name suggests, in top truncated ballots, respectively bottom truncated, a complete ranking of top or respectively bottom elements is provided, with all remaining elements being pairwise incomparable. So now how might we go about computing the necessary winners with all of this background? We are going to use as our starting point an algorithm that was proposed by Xia and Conitzer in 2011. An example of a preference is given on the right. The intuition here is that what we're after is to check whether a particular candidate C is an NW, and we can do this in polynomial time. This algorithm is going to run a competition between C and every other candidate. And it relies on computing two sets, up of C and down of C. I'm showing an example here. So if our candidate is Z, then the up of C is X and Z itself. That's the set of candidates that are ranked higher than Z, including Z itself. And the down is Z, T, U, and V. So that's the set of candidates to which Z is preferred, including Z itself. Now, what are we going to do in our implementation? Our method is going to depart from algorithm 1 by Xia and Conitzer in that we're going to be computing the entire set of necessary winners in one shot. The key ideas here are to reuse and reorder computation to enable early pruning and to efficiently compute up C and down C for specific types of preferences that I discussed. And these are partial chains and partitioned preferences. Does this work? We ran experiments, and I'll tell you about the data sets over which we run these experiments a little bit later. Here I'm showing a representative experiment where we look at the impact of the number of voters and the number of candidates on the running time of our optimized NW algorithm. We take 100 candidates, vary the number of voters between 10 and 10,000 on a logarithmic scale, and show the running time for each of the rules, plurality, to approval, and border. And for each family of synthetic data sets that I will discuss in a little bit as box and whiskers plots. We observed that the computation is efficient. A particular data set that I'm calling RSM mix represents the most general class of preferences, and it's the most challenging. It completes in 10 seconds or less, even for 10,000 voters across all scoring rules. And this running time increases linearly with the number of voters. Next, we analyzed the speedup that we achieved by optimizing the NW computation for 10,000 voters with the number of candidates ranging from 10 to 200 on a linear scale. And again, for the same 3 positional scoring rules, we observed that performance is improved by a factor of between 10 and 20 in most cases, and that these improvements are particularly substantial for partial chains and partitioned preferences that we treat differently. We discussed NW. Now let's talk about how we might compute the possible winners, PW. Here, for some cases, as we know, there are polynomial time algorithms. And for other cases, for every positional scoring rule except plurality and veto, we are in the case of NP completeness. For the polynomial case, we build on an algorithm by Betzler and Dorn, proposed in 2010, who modeled preferences as a network flow problem with two layers and integral capacities along network edges. We optimize their proposed algorithm to enable early pruning, and we also adopted to veto. PW for rules other than plurality and veto is NP-complete, computing PW. Our key idea here is to use a multi-phase computation, three-phase computation specifically, to progressively identify possible winners and prune clear non-winners. The outline here that I will discuss in a bit more detail is that in the first step, we reuse the insights that we developed for NW to help us with part of the computation for PW. In the second phase, we will heuristically construct winning completions. And then in the final third phase, we're going to do something that is the most expensive, and that is construct and solve an ILP for PW. A bit more detail here. The first phase is to use NW for PW. We run the NW algorithm on C to compute the necessary winners. They are also going to be possible winners, because if a candidate wins in every completion, they also win in some completion. Further, we identify and prune clear non-winners. We call them C1 loser here, as I said. And then we pass the remaining candidates, those that are not necessary winners and not clear non-winners, to phase 2. In phase 2, we heuristically construct winning completions. For each candidate that we consider at this round, we construct a complete voting profile in which it is a winner. And candidates for which we're able to construct such profiles are going to be added to the set of possible winners that we compute during this phase. And then we pass the remaining candidates, called C2, to phase 3. Phase 3 is to construct and solve an ILP. And once we've done that, we are going to add all identified winners to the set of possible winners that we return. How effective is this three-phase computation? This is perhaps the most interesting insight, experimental insight in my talk. We measured the effectiveness of each phase of this three-phase computation, and I presented in the table here for toApproval and Borda over partial chains, partition preferences, and the most general preference profile that I'm calling RSM mix. We measured the percentage of candidates that are pruned at the end of each phase here. And of course, the more we prune, the better, because the earlier phases are less expensive to run. We observed that on average, 99.18% of the candidates are pruned after the first two phases that run in polynomial time in the number of candidates. And specifically, we make two key observations here. Phase 1, and that is reusing the NW algorithm, is most effective when there are few possible winners. And RSM mix, the most general preference type, is the toughest data set to handle, and it needs phase 3 that requires ILP construction and solving the most. But overall, as we can see, this method in fact is effective. Very few candidates reach the expensive phase 3. Here I'm showing an empirical result, another empirical result, and that is the running time of three-phase computation on the set of possible winners on toApproval. Among the 75 instances in A, only 13 needed to execute the ILP solver. And we see similar results also in figure B. Figure C shows a comparison between our three-phase computation and the polynomial time algorithm that is based on network flow. And here we vary the number of partitions in each instance. And what we show also is that our three-phase computation outperforms the polynomial time algorithm that was given in the literature. The running time increases with the number of voters as expected. So here I'm showing some more results. I'm showing for the border rule now. The running time as the number of voters increases from 10 to 10,000, and on fixing candidates to 25. And on part B, I'm showing the trend in the number of candidates for 10,000 voters, which is the most challenging setting. The running time increases linearly with the number of voters, as we observe. And interestingly, partial chain datasets take as long or longer to process as the most general dataset, that's RSM mix. And this is because phase 1 of the three-phase computation turns out to be more effective for RSM mix. So now let's rewind. What are these experimental data sets that I've been talking about? We used two real data sets. One of them is called Travel, that is based on Google's travel review ratings. We collected it with the help of high school students who spent the summer working with us on a project. And the second real data set, called the Dessert dataset, was collected by us through an IRB-approved study, where we collected preferences of some 228 users about what desserts they prefer. And we're happy to share this dataset with you, or any of the other datasets. We saw some interesting cultural differences in people's preferences for desserts. The perhaps most important and most interesting dataset here, and I'm going to wrap up, is a synthetic benchmark that we developed called the Repeated Selection Model, or RSM. RSM is a novel generative model for partially ordered sets. It's inspired by the Repeated Insertion Model, or RIM, that is due to Donnion and co-authors, which is a generative model for rankings that has the Mellows model as a special case. RSM generalizes earlier generative models via a suitable choice of parameters. And intuitively, the way it works, and I'll stop here, is that it iteratively selects and removes a random candidates, and then randomly chooses whether the selected candidate succeeds each of the remaining candidates. There are more details here and in the paper that I don't have time to get into. To summarize, our goal here was to develop practical methods for NW and PW. Our methodology was based on the simple observation that one size does not fit all. We have to look at the data and develop custom approaches. We empirically evaluated performance, collected real data, and also developed a very interesting synthetic benchmark that is of independent interest, we hope. Additional details can be found at this link. This paper will appear in the next issue of the Transactions on Data Science. And this is off topic, I'll end with this. I've been developing scientific comics, check them out, on AI. And these are general audience comics. So check them out and please share. Thank you very much.
Thank you very much, Julia. I think we can.
I'll stop.
You can all mute our microphones and make a round of applause. Deserve it.
Thanks.
So the talk was very clear, and we had no question at all for the moment. So is there any question? It was too clear. Oh yes, Peter.
Yes, very clear and interesting talk. From the description you gave, are there any voting rules for which the issue is not yet settled, whether possible winner determination is either in p-time or hard? So or do we have dichotomous results in this field?
So the results are summarized here. So this is essentially what we understand at the moment. And Benny and Fokion, if you have anything to add here, please jump in.
Yes, with these problems are settled for the class of pure positional scoring rules, which are the rules that have this property that the rule for n candidates is obtained from the rule for n-1 candidates by adding some number in the scoring rule. So for this class of rules, it is settled. We know that veto and plurality, well, this is a sequence of papers. Veto and plurality, it is polynomial-time, all the rest it is empty complete. And we assume that the numbers are co-prime. If you just multiply all the numbers by some number, and then you get an equivalent rule. With necessary winners, this is all polynomial time. So the class of rules that are open are the non-pure ones. And I'm not aware of any natural example of a non-pure positional scoring rule, but for these, this is open.
It is not covered by a general dichotomy result from the database area.
And, well, it's not from the database area. It comes from the COMSOC area. We are just using these results. Yeah.
Okay.
Julia, just a clarification, if I may. There is a typo in this slide because the partial chains do not subsume partition preferences. They are incomparable. Partition preferences subsume doubly truncated, but partial orders are incomparable to the other. And in response to the previous question by Peter, there is a complete classification for the possible winners on partial chains, but not entirely on partition preferences. This is the work of Batia Koenig. There are some gaps in the complete classification. The point, however, is exactly what Julia said, that even in the restrictions, you come across NP-complete cases.
The typo is addressed. Thank you, Fukion.
Okay, so we have some questions in the chat. Some question about the data set, which you have started to answer them, but perhaps another question by Mark Wilson, whether your data set will be on preflib at the end.
Yes, we should definitely put it on preflib. And the Rsm model is due to Theo de la Mazur, who is on this call as well. So if you have any specific questions about that, do please address them to him. I think it's a really, really important and interesting contribution of this work. And we will be happy to make the dataset available to you guys on request, but we will also work to put it on preflib.
And a comment by Dominic also on this problem. Not sure preflib supports partial votes. I don't know if anybody has an idea about this.
Yeah, I mean, as far as I know, they collect real data sets rather than synthetic benchmarks, right? So for us, what we do is actually provide the machinery to generate data sets under the parameters that you specify.
Bill, you had a question too?
Yes, if you look at the kind of partial preferences you're considering, which you have atomic information, a certain voter prefers a certain candidate X to a certain candidate Y, then there's a mathematically natural way to apply Borda directly to that without completing the votes. You simply give, every time one voter prefers X to Y, you give X plus 1 point and Y minus 1 point. And if they happen to be linear orders, then that's the same as regular Borda. And it's a C2 method, so Borda is rather special in that you can't say this about any other scoring rule. So I'm wondering whether you found any links between that version of Borda and possible and necessary winners.
I haven't thought about this, but maybe others can jump in.
Well, I think, Bill, thanks for the question. I think the answer is no, we have not considered this. We followed the model of Jérôme Lang and Catherine Konjak in considering all the completions and taking we worked with the notion of possible and necessary winners. What you suggest, it removes the incompleteness by basically changing the rule in effect, right? You're just applying it to the partial orders that you have.
That's right. Yeah. Doesn't even have to be a partial order.
That's right. Yeah.
But there's an argument that it's actually the same rule. It's just a natural extension of the rule.
But that also assumes a particular kind of a completion, right, of the partial order. Essentially, it says that whatever candidates do not appear in the completion are going to be at the bottom.
No, because you get minus ones as well as plus ones. They'll tend to be at the middle.
I think it's just a model where you don't necessarily assume that the partial order means incompleteness. A partial order is a partial order, and it allows to apply the border rule. Whereas in our the work that we've been focusing on, this is always a representation of many completions. So
I understand. I'm just there are two natural approaches. I'm wondering if they're related at all to each other. That was the question.
We have not looked at it. It's a very good question. Thank you.
Some comments in the chat. Okay.
Yeah, so the dessert data set is also discussed by Theo, who collected it. And this is a very interesting data set as well that we constructed specifically to allow people to express uncertainty in their preferences as a very cute UI.
Maybe just short comment from me. I think I read in the New York Times that for the New York primaries, it is STV that will be used, or what you call rank choice and stuff like that. So do you agree with me? So it's So the example is not, it's not too approval. You're right.
Yeah, we are using single transferable vote, and the city is trying very hard to explain to people what that actually even means. And there is a very large number of candidates, so it's going to be very interesting to see for us and to study how this selection plays out, in fact.
So we're waiting for part 2 with the New York example.
That's right.
And you mentioned that you developed a model to generate profiles. And I know that, well, usually when you use a different assumption to generate random profiles, you may end up with different results or different type of results, or the order may change. Have you tested other models and the RSM model that you put forward?
So here's a little bit more about the RSM model, and Theo, do please feel free to speak up. The model essentially has 3 parameters that we can set. One of these is a reference ranking of candidates of length m. The second is a probability function, and that is a matrix pi. And the third is a preference probability function p. And so by setting these parameters in particular ways, you are able to get a wide variety of profiles. And then there are also some very interesting special cases that you could get.
So you can come back to the classical impartial culture, impartial anonymous culture, mallows, or stuff like that?
Right, we can go back to RIM very easily. RIM you use to generate mallows. RIM is an efficient sampler for mallows. And then you can generate top truncated orders, for example. You can generate partial chains. So it's a very general data generation method. And in the paper, we compare the types of preferences we derive with some other generative models that have been proposed in the literature. For example, Gerlein had some proposals, and we compare to him.
Good. So I think we are done, unless there is one last question. No. So we can thank again Julia.
And everybody else who helped answer. Thank you.
And we can move to the... Thanks, everybody. So we're moving now to the second speaker, and the second speaker is Simina Brânzei. So Simina, the floor is yours. Please share your screen, and the floor is yours. Your microphone.
Simina. Oh, sorry. Can you hear me now?
Great.
Okay, thanks. Okay, let me see how we can manage to do this. Can you see my screen?
Perfect.
Oh, it's not full screen mode. Okay, so I have 20 minutes, right?
That's it.
Okay. So thanks for inviting me. I'm going to talk about the K-cutting problem and the connections with sorting and searching in rounds that we found while studying it. And this is based on a paper with Dimitris Paparas and Nicolas Recker. So the outline will be that I'll start by describing the K-cutting problem and what the rounds of computation look like here. Then I'll mention a sorting problem with rank queries that turns out to be equivalent in some sense to proportional K-cutting. And then I will discuss 2 basic search problems and duality gap that we find there. So the K-cutting model is that we have a resource, which is called a cake, that must be divided among n players, each of which has private valuations. And the cake is given by the interval 0, 1. Each player I has a value density function vi, and a piece will be a finite union of intervals that they may be disconnected. And then the valuation of a player for I for some piece x will be the integral vi over x, and we'll denote it by vi of x. And we can, without loss of generality, normalize so that the value of player I for the whole resource will be 1. So then an allocation will be a partition of the cake into disjoint pieces so that they sum up to the whole cake. So in some works, it's also okay to throw away the resource. The fairness criterion that I'm going to focus on today is that of a proportional allocation, where each player I has value at least 1/n for the piece that it receives. Most of the fair division algorithms are formulated in a query model due to Robertson and Webb, where there is the mediator that tries to find a fair division, interacts with the players via queries given by cut and evaluate. So in a cut query, we ask a player I, given a value v, the player must return the point x such that the value of player I for the piece from 0 to x is v. And in an eval query, player I, given a point x, player I must return the value v such that its value for the piece from 0 to x is v. And to make this more concrete, so this is a simple example which implements the basic cut and choose protocol. So here we have two players, Alice and Bob, and the mediator asks Alice to cut the cake in two, which is implementing by asking Alice a cut query at 0.5. So that means that Alice indicates a point x where the cake is divided into equal pieces. And then Bob is asked to pick its favorite piece, which can be implemented by asking Bob an eval query at the point x, which was generated by Alice in the previous step. And then Bob evaluates the left piece. Let's say it's 1/10, so then he will prefer the right one that the mediator can give it. So in this work, we are going to look at rounds of interaction, which are also known as rounds of adaptivity in some settings, where basically the algorithm is allowed a budget of rounds of interaction with the oracle. And in each round, it can submit a set of parallel queries. So the way this works, if we think of one round, which is the extreme case of k = 1, then all the queries that are ever asked must be submitted at once. And then we get back the answers, and then we must find a fair division, for example. When k is infinity, but depending on the problem, it might not need to be infinity. It might be enough that it's n squared or 2 to the n or something like that. Then this corresponds to the fully adaptive setting, where the queries can be submitted one by one, and we have no upper bound imposed. The question is, how many queries are needed to compute a fair allocation in k rounds when we have k rounds of adaptivity? When we think of algorithms in rounds, this actually captures also a distributed setting where we can view an algorithm. So this happens when we optimize. If we design an optimal algorithm that runs in k rounds, then what usually happens is that we will want to equalize the amount of work done in each round. So with that, we ask the same number of queries in each round, and that will correspond to seeing an algorithm in k rounds as we have a central machine that issues in each round some queries, one to each processor, and then it waits for the answers before issuing the next set of parallel queries in round j+1. So here in yellow is the central machine, and it issues its queries, one per processor, and then it waits back for the answers, and then it issues the next round of queries. So then the query complexity in k rounds is equivalent to determining how many processors are needed to achieve a parallel search time of k for whatever problem we have. Like here, we want to find a fair division. And this is relevant for settings where each query takes work to do, like in the fair division problem, it needs to find an integral, for example, to compute it. In other setting, the players might have to do some other computation that is challenging. So there is a lot of literature on fair division and k-cutting in particular. There are several books. Sorting and selection in rounds have been studied since the 70s, and there is also recent work, and there is a book from 2014 that summarizes it. The rounds of adaptivity have also been considered in optimization with the aim to understand the parallel complexity of optimization. So this is from the 90s. Starting in the 90s, there is also recent work there. And then other settings where rounds of interaction are expensive, I'll mention two of them. One is in fault detection, where we want to identify all the defective items from a finite set. And then the queries that we have available is that, So we are given a subset of the items, and then we get yes or no to whether there is something defective in that set or not. So an example that is actually was done at least in some places when testing for COVID infections is that you combine the samples into a pool, and then you check if that set contains an infection, and if yes, then you zoom in and you repeat. So, and another one is active learning, where there is a so-called active learner that can submit queries to be annotated by a human oracle. And going back every time to the human oracle and asking one more question takes effort, and the human would prefer to have fewer rounds of interaction if possible. So an informal result is that computing a proportional allocation with contiguous pieces in the standard query model, which is known as Robertson-Webb for k-cutting, is equivalent to sorting in the rank query model, which was studied by Alon and Azar in '88. And this holds for any number of rounds. And the query complexity is theta of k times n to 1 plus 1 over k for k rounds. So I should also clarify in the rank query model. So we are given an array X with n elements, and we have access to an oracle that answers queries of the form, how is rank of xi compared to k? And let's say the answers can be strictly less than, equal, or strictly greater than. So all these, one other version is that we have strictly less than or greater equal. So all these versions are equivalent within constant factors. And Wöginger and Skal, in fact, gave a lower bound for proportional k-cutting for the fully adaptive setting. And their construction does most of the work of making the connection with rank queries, or sorting with rank queries. They don't explicitly call it sorting with rank queries, but they do discuss the sorting problem, and they basically construct partitions where we care about the rank of elements. Are there any questions so far? Okay, I cannot see the chat, so let me know if there is anything I should answer.
Nope, I don't see any questions.
Okay, so and another note I want to make is that the rank query model for sorting has also been studied, and the lower bound for randomized algorithms was given by Alon and Azar in '88. And in this work, we give a lower bound with a better constant for deterministic algorithms and also some upper bounds. So this is a visual depiction of the reduction that was that appears in the work of Wöginger and Skal, and that we formalized to contain rank queries. Given an array X with n elements, and we can access the array via rank queries, where we ask how is rank of the element xi compared to k for some integer k from 1 to n, and then given such an instance, we construct from it a fair division instance with proportional k-cutting instance, so that basically any lower bound for the sorting instance will also apply to k-cutting. So I'll briefly mention the algorithm for proportional k-cutting in rounds. Basically what we do is in each round, like if n is the size of the number of agents, we ask each agent enter 1 over k equally spaced queries, where here we'll have to take floor and ceiling. So I'm omitting that notation. And this will divide the cake into enter 1 over k subcakes that will have equally many agents assigned to each, or roughly equally many. And then we are going to recurse on each subcake in parallel. So here we have a picture with the original cake that everybody is kind of initially assigned to. And then in round 1, let's say in this case, we divide into 3 small cakes. So by asking each agent to divide the cake in 3 pieces that are equal to each of them. And then that will automatically move the agents into one of these cakes, whichever one is more interesting to them. And then we repeat, and this can be done in parallel. So we get that the number of queries is asymptotically k times n to 1 plus 1 over k times some constant. For the lower bound, we basically combine these two prior results that I mentioned. So we combine the reduction from sorting with rank queries to proportional k cutting by Vöginger and Gall, and the lower bound on sorting with rank queries given by Alon and Dazar. We also studied two basic tasks in the rank query model that are related to sorting. So these are locate and selection. So in the selection problem, we are given a vector x, which has n elements, x1 to xn, and an integer q, which ranges from 1 to n. And the goal there is to find the element xi that has rank q. So for example, if q is equal to 1, then the task is to find the minimum element in the vector. If q is n over 2, then we want to find the median. If q is equal to n, we want to find the maximum. And in the locate problem, this is kind of like inverse selection. We are given a vector x, so with elements x1 to xn, and an element xi, and the goal is to find the rank of element xi. And so it turns out that select and locate are actually equivalent to two even simpler problems in some sense. I mean, I guess the level of complexity is the same, but they seem simpler. So I'm going to explain this, how that is the case. So the search problem will be that we have a vector x and an element z, which we are promised is in the array. And the goal is to find the location of z. So basically we know that z is equal to 1 of x1 to xn, and we want to know which one of these it is. And the catch is that we can access the elements of x via comparison queries. So these queries are of the form, how is element z compared to xi, or how is xi compared to xj? And the answers are, without loss of generality, strictly less than, equal, or strictly greater than. So this is an example of a vector, x, with some elements, and the element z we're looking for. And we basically cannot open up the box to inspect the elements of x and do Boolean operations on them, but instead we can access via comparison queries. And the vector x can be sorted or unsorted. So, and in fact, if it is unsorted, then the queries, it's not very useful. A comparison query is not very useful beyond telling us whether z is equal to the element xi that we asked about or not. While if it is sorted, then we get more information from such a query. So again, we will look at rounds here at search and rounds, where the algorithm will have k rounds of interaction with the oracle that answers comparison queries. And so one example that I was talking about why you may want to use a different processor for each query. So if you are, I don't know, analyzing some genomic data, and you're searching for some gene or something like that, or some kind of pattern, then that may take a long time, and you may want to execute each such query on a separate processor to speed up the computation time. And so I'll talk first about search when the vector x is unsorted. So this is known as unordered search. So we are given the vector x and the element z promised to be in the vector x. And our goal will be to find the location of z with success probability p via at most k rounds of interaction with Oracle that answers the comparison queries. And I should mention that a small probability of success is still interesting. So for example, if you want to break RSA, then you might be happy even if the success probability is 1 over 10. If by doing so you obtain some goal that you had in mind. A first observation is that unordered search with comparison queries is equivalent to select with rank queries. And the proof idea is roughly the only type of comparison in unordered search is comparing the searched element z to the element at index I in the vector x, so to the element xi. And what we learned from that is if xi is equal to z, this gives us the answer. And otherwise it eliminates the location I without providing further information on the other indices. And it actually turns out that also in select, every query is either for the correct item or it eliminates the item without providing further information on the other items. So the first result we have for unordered search is for randomized algorithms. So this is for on a worst case input. So we get that an algorithm that, any algorithm that succeeds with probability P and runs in K rounds, asks in the worst case at least NP times K plus 1 over 2K minus 1 queries in expectation. And this bound is tied with an additive one. So there is in fact an algorithm that asks at most NP times K plus 1 over 2K queries in expectation. And the randomized algorithm will be very simple. With probability 1 minus P, we don't do anything. And with probability P, we run an optimal deterministic algorithm, this will turn out to be as follows. We query N over K items in each round, where these items are chosen deterministically in some arbitrary way from the remaining unqueried ones. So it can be the ones with the smallest index lexicographically. And for the lower bound, we had a surprise here. So first we thought that we can use Yao's lemma to prove lower bounds, but it turns out we can only do that when P is equal 1. So if P equals 1, then we do get a lower bound by using Yao's minimax lemma. And so we know that the expected cost of a randomized algorithm on the worst case input is no better than the expected cost of a deterministic algorithm on a worst case probability distribution, where the deterministic algorithm is optimal for that distribution. So basically, when P equals 1, it suffices to establish a lower bound for randomized algorithms to find an appropriate distribution of difficult inputs and then prove that no deterministic algorithm can do too well on that distribution. And it will turn out that for search problems, the uniform distribution is the worst case. When P is strictly less than 1, we have two parameters in some sense. So this makes the problem multidimensional, and we get a kind of duality gap in Yao's lemma. So we prove the lower bound directly by induction, and we will study separately deterministic algorithms on random inputs. So for deterministic algorithms on random inputs, so here again, we have the unordered search problem. So we have some vector X with n elements and an element Z that is promised to be in the vector. Then we have that any deterministic algorithm that succeeds with probability P and runs in K rounds asks in the worst case at least NP times, and then we have this bracket with 1 minus K minus 1 over 2K times P. And then everything minus 1 queries in expectation. And this is also tied with an additive one. So there is a deterministic algorithm that asks this many queries, the main term here. And we know that the uniform distribution is the worst case for unordered search. It will actually turn out to be the worst case for ordered search too. And to say what is this optimal deterministic algorithm, basically I mentioned it. It follows from what I mentioned earlier. So basically what we'll do is that in each round, we're going to query NP over K, or floor of NP over K items, which will be chosen arbitrarily from the unqueried ones left at that point. So this is a picture. So in blue, for unordered search. So in blue, we show bounds for deterministic algorithms on a uniform random input. So the expression for what we plot. So basically we plot, they are within, so actually this plots both the upper and lower bounds for both deterministic and randomized, but because they are very close, like with an additive one, they appear as only as 2 curves rather than 4. For deterministic algorithms, we have this term NP times bracket 1 minus K minus 1 over 2K times P, close bracket. And for randomized algorithms on a worst case input, we have NP times K plus 1 over 2K. I guess I should also mention briefly what it means for deterministic algorithms to search on a uniform random input. So it means here that the algorithm is searching, the algorithm is deterministic, but it's given an element that is a uniform random element from the array to search for. What we found interesting here is that for deterministic algorithms, the expression is quadratic in P, while for randomized on worst case input, it's linear in P. So we also get a corollary for the fully adaptive setting for unordered search. So this is obtained when k is equal to n. And the bounds that we get roughly are for deterministic algorithms, we get p times n plus 1 over 2 with plus minus 1. And for randomized algorithms on worst case input, we get p times n minus 1 over 2 times p, also plus minus 1. I'll briefly mention also what we found for ordered search. So here we additionally know, so we are given a sorted vector x and an element z promised to be in x, and the goal will be to find the location of z via k rounds of interaction with success probability p. So here the search can be done faster in the fully adaptive setting. So if, for example, if p is 1, if success probability is 1, then this is like binary search in the fully adaptive setting. So k will be at most log n. An observation again is that ordered search with comparison queries is equivalent to locate with rank queries. So locate is a problem that I mentioned earlier that we started looking at in the rank query model. So in locate, we're given a vector x and an element xi, and we want to find its rank. And the proof sketch is that we can map the locations in the locate problem to the elements in the ordered search problem. So there are various applications of rank queries if you want to look into it, like if we have some kind of database with students and student IDs and grades, and we want to ask if the rank for the grade that a student obtained less than 10, for instance. So for the ordered search problem, for deterministic algorithms on worst case distribution, which will again be uniform distribution, we get that the query complexity is theta of k times p to 1 over k times n to 1 over k in expectation. And the deterministic algorithm will be to divide the array containing the first np elements into np. Sorry, so that, yeah, that's there should be a bracket there. So it's np to the power 1 over k blocks, and then we recurse. And then for randomized algorithms on a worst case input, the query complexity is k times p times n to 1 over k. So you can notice the difference between these expressions is that for deterministic algorithms on random input, the expression in p is p to 1 over k, while for randomized algorithms on worst case input, the expression in p is just p. Okay, and the randomized algorithm here that is optimal is with probability 1 minus p, we don't do anything. And with probability p, we divide the array into n to 1 over k blocks and then recursively search in each block. So this is a plot where we plot these two expressions. We plot the actual bounds that we get. So with blue, we get something like 4k times p to 1 over k times n to 1 over k. So in blue, we have the bound for deterministic algorithms, and in red for randomized algorithms. And the curves meet at 0 and at 1. So the success probability we're interested in is 0, then we don't need to do anything. So the query complexity is the same. And also if p is equal to 1, then they also coincide. So there we can use Yau's lemma, and they meet, like the query complexity is the same for randomized on worst case inputs and deterministic on worst case input distribution. And again, we get a corollary for fully adaptive. So fully adaptive setting, which is obtained when k is log n. So for deterministic on uniform random input, we have log n times p to 1 over log n. And for randomized algorithms, in the worst case, it's p times log n. So there may be other settings where rounds of interactions make sense in a resource allocation including infer division, like for example, computing an NV-free solution or epsilon NV-free or equitable division. And there may be also other problems where this kind of duality gap appears and may be quantified. So I'll stop here. Thank you.
Thank you very much, Simina. So you can mute your microphone and you can give a round of applauses.
Thank you.
So do we have any questions? Nope. No question? Okay. So sure, nobody has any question to ask? Okay. So I guess you can ask question if you wish or discuss with Simina privately. So we have a series of announcements then. The first one is that after the talk, Reshef and Bill invite us to go to Gather Town to check the interface for the poster session of the next COMSOC seminar, workshop. Pardon. So I will just put the link again on in the chat. And while I'm doing that, I'm leaving the floor to Hule, who will announce the next seminar.
Yeah, thank you. So we're going to have the next seminar in 2 weeks' time at the same time of the day. Our speakers will be Eric Packett and Nicolas Maudet. We don't have the abstracts yet, but I'm still very confident it's going to be wonderful, and I hope to see many of you there.
Oh, here is the link. Dominic has been faster than I. Okay. So if everything is set, I will say hello, goodbye to everybody, and we will meet in 2 weeks from now. Goodbye.
Bye.
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 Thank you, everybody. Bye.
Bye.
Yeah, I don't want to cancel the Zoom meeting because I was criticized last time for doing it too early.
The reason you don't want to do it is because you did it too early. It's not because you were criticized for doing it too early, though.